Where am I? There we go. Okay. So let's just get off of the slides just for a brief moment here. And I want to talk to you about hybridization just for a second. All these details are in the slides, but I just want to walk through it with you, okay, kind of quickly. So if we think about carbon, which is what we're focusing on, it's 1s2, 2s2, 2p2. So it's got 4 valence electrons. And earlier on, we drew the Lewis structure of carbon, and we said 1, 2, 3, 4 unpaired electrons like that. However, there is a problem with this. There's a disconnect between this concept, which everybody accepted, and this concept. Let me explain to you why there's a disconnect between the two. If we focus on these valence electrons and we say in a 2s orbital, I have 1, 2 electrons, and then I have 3 2p orbitals, and I have 1, 2 electrons like this. Well, in this Lewis structure, we have 4 unpaired electrons. But here we only have 2 unpaired electrons. And then we have 2 that are paired up. So how do we reconcile this? The carbon has 4 unpaired electrons because our electron configuration doesn't match. So here's what we do, is we take one of the electrons out of the 2s and we move it up into here. But then we say, well, that wouldn't solve the problem either, because if I did that, this is what it would look like. I'll just move this. I'd have something that looks like this. Now we've got 4 unpaired electrons, but what's the problem with that? That would look pretty messed up, okay? You'd have a carbon with an s orbital on it with an unpaired electron, and then you'd have 1, 2, 3 p orbitals like this. So those 4 electrons wouldn't be spread out evenly like they are in this Lewis structure here. So now, how do we fix that? The way that we fix that is we hybridize the orbitals. What does hybridize mean? If you think of a hybrid car, it's a car that runs on gasoline and electricity. So what we're going to do is we're going to hybridize these orbitals. We're going to take the 1, 2s and the 3, 2p's. What's 1 plus 3? The answer is 4. So we're going to get 4 degenerate or equal energy orbitals. And now we've got the mixture that came from 1s and 3p's. So we're going to give it a new name. We're going to call it sp3. Okay, 3 p's were used to make it, and 1s. So 1s and 3 p's, sp3. Now, if you're wondering, why don't you call it 2sp3? Because they both had the principal quantum number of 2. We just leave that out of it. Okay, we just leave it out. It's a convention, but you could put it in technically. So now we've got 4 degenerate orbitals, 1, 2, 3, 4, and they each have an unpaired electron in it. Now, what does an sp3 orbital look like? It kind of looks like this. It's got a big lobe, and then it's got a small lobe like that. However, we usually just leave the small lobe out like that. So we just say, this is the orbital, and we actually label it. Okay, so we're going to write sp3 on that. So now what's it going to look like? Our carbon is going to look like this. Here's our carbon atom. It's going to have 4 sp3 orbitals on it. 1, 2, 1 in the back. See, I'm trying to draw a tetrahedron here. And then 1 coming out in the front. We'll kind of shade that 1 in here. And then we'll just label them sp3, 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 and sp3. They each have 1 unpaired electron. And now we can wed these 2 ideas, that the carbon has 4 electrons evenly spaced around it based on hybridization. So when carbon has 4 single bonds, as it does in the molecule of methane, which is the simplest organic molecule in the universe, okay, when carbon has 4 single bonds, it's sp3 hybridized. So that's a little tiny review of hybridization. Again, this is a review of General Chemistry 1, so you should have seen this in General Chemistry 1. But if I go back to my slides, okay, you'll see that this is covered in detail in my slides as well. So it says here the ground state electron configuration for carbon can't explain how it makes 4 bonds. So to review, what's the ground state electron configuration of carbon? It is 1s2, 2s2, 2p2. So you have 4 unpaired electrons. However, you have 2 in the 2s orbital, and then you have 2 in the 2p. In this orbital diagram, they actually included the 1s electrons, but those are core electrons, so we're not going to worry about that. So what we do is we move one of the electrons from the s orbital over to a 2p. I said we promoted it. The word they used here is excitation, and there's nothing wrong with that. However, what's the problem with this is that now you have 4 unpaired electrons, yes, but they're not all in equal orbitals. You have 3 in a 2p, the 3 in 2p's, and 1 in a 2s. So what we have to do is we have to hybridize them. We have to mix them together so that we end up with 4 electrons evenly spaced around the carbon. So here's the hybridization. So we take our 3 2p orbitals here and the 1 2s, we hybridize them, and we end up with 4 degenerate sp3 orbitals. And this explains why carbon has 1, 2, 3, 4 evenly spaced electrons around it. So there we go. So again, how do you draw the sp3 hybridized orbital? Well, usually we draw as it's shown here in the bottom. We have our carbon, it has one big orbital, and then we have a smaller orbital. They put it pretty big here. But normally what we do as chemists is we just leave this out completely. We don't even draw it. We just draw the big side and we say sp3 because that way the person knows exactly what type of orbital it is. We give them the answer. We tell them this is an sp3 orbital. Sorry, I missed my spot. There we go. Okay, so now we have our sp3 hybrid orbitals. So the answer is this. Whenever you see a carbon that has 1, 2, 3, 4 single bonds, it is sp3 hybridized. So here is my carbon. This is an sp3 orbital. Hopefully you can see my writing. Maybe I'll try the blue pen. This is an sp3 orbital. This is sp3. This is sp3. And this is sp3. This is a tetrahedron here, trying to show you how all 4 of these, which look like balloons stuck to the carbon, those are all evenly spaced around the carbon, and they actually adopt a tetrahedral. So this is a tetrahedral arrangement. Tetrahedral. Now hydrogen doesn't hybridize. It's just 1s1. So 1s1. So this is an s orbital. This is an s. This is an s. This is an s. So if you remember earlier, I said, what's one of the ways you can make a sigma bond is when an s orbital overlaps with the head of a p orbital. And that's what's being shown here, 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 and here. And so those are 4 sigma bonds. This is a sigma bond. This is a sigma bond. This is a sigma, and this is a sigma. Again, if you're confused and you're like, what the heck is this? Okay, what that is this is just showing a molecule of methane, CH4, okay, which has 1, 2, 3, 4 sigma bonds. So the carbon is sp3 hybridized. Now, how do we recognize carbon as being sp2 or sp hybridized? Well, in that case, we look at the total steric number. Now, if you don't remember the concept of steric number, so steric number, the way that we calculate steric number is a single bond can contribute a steric number of 1, a double bond contributes a steric number of 1, a triple bond contributes a steric number of 1, and a lone pair contributes a steric number of 1. So when your carbon has a steric number of 4, so we've got 1, 2, 3, 4 single bonds, 4 sigma bonds, either way you want to look at it, that means the carbon is sp3. Now, based off of what I told you, in this molecule here, could anybody tell me what's the steric number of that carbon? Based off of what I said, it's got 2 single bonds and 1 double bond. What is its steric number? Anybody? A single bond counts for 1, a double bond counts for 1. So its steric number is 3. Exactly. So we'll just say Sn for steric number is 3. So when carbon has a steric number of 3, its hybridization is not sp3, it's sp2. Okay? Now where does sp2 come from? Well, where it comes from is if you look at that carbon, it's got 1, 2, 3 sigma bonds, but then it also has a pi bond. If you remember, a pi bond comes from the side-to-side overlap of two p orbitals. And so those orbitals are not hybridized. So how do we reconcile that? Okay, we go back to our carbon, which is 1s2, 2s2, 2p2. Okay, we're going to take one of the 2s electrons. We'll put it in a 2p orbital. So that's what you see right here. One electron in the 2s, 3 in the 2p's. Now you've got 4 unpaired electrons, but we need 3 sigma bonds and 1 pi bond, right? We're trying to make this carbon. It's got 1, 2, 3 sigmas and 1 pi. Okay, so what we're going to do, you see the dashed circle here, or the dashed oval? We're hybridizing 3 orbitals to make 3 degenerate sp2 orbitals. Why are they called sp2? Because they're made from 2 p orbitals and 1 s orbital. So we get 3 sp2, and then we have 1 2p orbital left over. Why do you need a 2p orbital? The 2p orbital is used to make the pi bond, right? And these ones are used to make the sigma bonds. Okay, because a pi bond comes from the overlap of 2, we'll use blue to be consistent, 2 p orbitals that are not hybridized. Okay, so if we have a steric number of 3, our hybridization is sp2. So what does an sp2 hybridized carbon look like? You've got 1, 2, 3 sp2 hybridized orbitals. What's the arrangement they're going to adopt? They're going to be as far away from each other as possible. And so we're going to have bond angles here of 120 degrees here, 120 degrees here, 120 degrees to that one in the back. So those are the 3 hybridized orbitals, the ones in gray. Those are your sp2 orbitals. And then the one that's shaded red and blue, that's your unhybridized p orbital. So now that we have that, if we put 2 of them side by side, we get our molecule of ethylene. Again, what we're trying to do is we're trying to make this molecule, or show where this molecule comes from. So if you're struggling to understand what's being shown on this slide, what this picture represents is nothing more than this molecule. Okay, it's showing you this molecule. Maybe I'll write it down on the side. Okay, I'll put it here. It's this molecule. Okay, each carbon has 3 sigma bonds and 1 pi bond. So let's take a look. When you overlap the sp2 orbitals with an s orbital, you get a sigma bond. Here's an sp2, here's an sp2, and the s from the hydrogen. So those give you the sigma bonds. So far, I've covered these 4 bonds. Now, what about the bonds between the 2 carbons? One of them is a sigma. That is this one. Okay, because you have the head-to-head overlap of this, be consistent with my colors, sp2 and sp2. Now, where does the pi bond come from? It comes from the overlap of the 2 p orbitals. You're looking at it and going, Mr. Dion, that's a p orbital, that's a p orbital. They're not overlapping. I agree. Okay, the way that it's drawn, they are not overlapping, but in reality, they actually are. If you were to draw them touching each other, it would be impossible to see this bond. So here's the workaround. Don't laugh. This is the way we do it as chemists, okay? We actually draw a line connecting the 2 orbitals, and that represents the 2 p orbitals touching each other, okay? If you're going, oh, that must be something you invented. No, I didn't, okay? All chemists, we do this. We draw a line to connect them, and we say, that's what it looks like. So in reality, yes, they are touching like this and like this. However, we draw them far apart. Okay, again, I'll draw it here if you don't believe me. I'll put it up on the internet so everybody can see it. Okay, we can draw them far apart like this and just say, well, actually, they're not far apart. They're actually touching like this, and it means, come on, you. It means the exact same thing. Okay, it's totally fine. All right, there we go. So that's a little bit about hybridization. And so to review, if you have a carbon that has 4 bonds, it's sp3 hybridized. If you have a carbon that has a double bond and 2 single bonds, it's got a steric number of 3. So therefore, it's sp2 hybridized. And if you have a carbon that has a steric number of 2, it's sp hybridized. All right, so now what we're going to do is I'm just going to move this out of the way because it's taking up valuable real estate. So I'll put it up here. There we go. And we'll talk about formaldehyde. Okay, I'm sure you guys have all heard of formaldehyde. It's used as a preservative. Formaldehyde is actually a gas. When they bubble it through water, it makes formalin, which people call formaldehyde. Anyhow, so if I draw the Lewis structure of formaldehyde, it looks like this. Okay, and it says identify the types of bonds that form the carbon-oxygen double bond. Okay, I'll get you guys to help me with this. The first bond between two atoms is always a what? What kind of bond?
Sigma.
Yeah, thanks. Awesome. The second bond is called a? Anybody? There you go. Pi. Great. Awesome. Thanks. Okay. Now it says identify the atomic orbitals that form each carbon-hydrogen bond. Okay, so I'm going to redraw the molecule here. So if I redraw it like this, we know that the steric number of the carbon is 3. Therefore, the carbon is sp2 hybridized. The hydrogen never undergoes hybridization. It just has the 1s orbital. So what type of atomic orbitals form those carbon-hydrogen bonds? Well, it's an sp2 orbital and a 1s. So we'll put here an sp2 and a 1s. We already answered this one, so it's a sigma and a pi. And then the last one is what type of atomic orbitals do the lone pairs occupy? So when it says lone pairs, it's talking about these two right here. So what's the hybridization of our oxygen? So let's go over this one, okay? And don't shout me out here. Trust me, this is important. You want to know this. So let's take a look at the electron configuration of oxygen. So oxygen has a total of 8 electrons. So we'll say here oxygen is 1s2, 2s2, 2p4. But we're really only concerned with the valence electrons because those are the ones involved in bonding. Okay, so if I draw a 2s orbital, it's got 2 electrons, and then I've got 3 2p orbitals, 1, 2, 3, 4. Now, if you're looking at what I've drawn here, you might say, hey, this is awesome. I've got the 2 lone pairs, then I've got a sigma bond, and I've got a pi bond. Everything's great. I need 1 electron from the oxygen to make a sigma bond, 1 electron from the carbon, pi bond, et cetera, et cetera. Well, what's the problem with this? Is that you don't have the 2 lone pairs, the ones that I have highlighted in green, they're not the same energy. One's in a 2p, one's in a 2s. So there's a serious problem with that. So what do we need to do is we need to hybridize our orbitals. So I'll just say here, hybridize, and we need to hybridize 3 of them. If you're saying, well, why aren't you hybridizing all 4? The reason you hybridize 3 is because one of these bonds is a pi bond. And for a pi bond, you don't use a hybrid orbital, you use an unhybridized p orbital, right? So we're going to have 3 degenerate sp2 orbitals, and then we're going to have 1 2p orbital that we left untouched. This is the one that's going to be used to make the pi bond, okay? So it's going to have 1 electron in it. So now we're going to have 1, 2, 3, 4, 5, 6. Sorry, am I miscounting here? So you can see that I have a total of 1, 2, 3, 4, 5, 6, right? Because we have 6 valence electrons. Sorry, I'm getting tired now. Anyhow, so what does this mean? It means that these paired up electrons, these are our lone pairs. Okay, this is the one used for her sigma bond, and the 2p orbital, that's the one used for the pi bond. So there you go. That's the answer. The lone pairs are going to be in sp2 hybridized orbitals. Now, what if we think about something like acetylene or ethine? Okay, so if we have a carbon-carbon triple bond, now we have 1 sigma and we've got 2 pi's. Okay, this is a pi, and this is 1 pen. There we go. And this is a pi. Okay, so what I'm going to do is I'm going to summarize the information that's on this slide, in this slide, I'm going to do it on a blank document. Okay, so just bear with me. I know I'm being thorough, but that's what we came here for, right? Is to learn the subject. So if we think about acetylene, okay, so I'll try this one more time. If we have a triple bond between our two carbons, it means the first bond is a sigma, and the next two are both pi's. So pi and pi, and of course this is a sigma as well. Okay, so that means we need 2 electrons in hybrid orbitals to make our sigma bonds, and then we need 2 in unhybridized orbitals to make 2 pi bonds. So I'll go through this a little quicker. So we have carbon, which is 1s2, 2s2, 2p2. Those are the valence electrons. 1, 2 in the 2s, 1, 2 in the 2p's, like this. But we need to hybridize these and leave the 2 electrons in the 2p's, but we need 2 degenerate electrons to make the 2 sigma bonds. So we're going to hybridize. I'll just do it going down this time. So we're going to mix 2 orbitals to make an sp orbital, and then we're going to leave 2 unhybridized 2p orbitals to make the pi bond. So we're going to have 1, 2, 3, 4. So these 2 electrons will be used to make the sigma bonds. These 2 will be used to make the 2 pi bonds. So now, what does a carbon look like that has 2 sp hybrid orbitals on it? It means you're going to have one like this and one like this. Let me move it over a little bit. Shoot. Come on, you. What am I doing wrong? There we go. Okay, we'll move it over a little bit like this, and we're going to label this, and we're going to say sp, sp, and they each have 1 electron in it. Okay, so it's going to have 2 sp hybrid orbitals that each have 1 electron. So now I've drawn these 2 guys, and now I'm going to have 2 2p orbitals. So I'm going to have 1 going up like this. I don't know if I'm drawing my phases the same way they are in the textbook. That's neither here nor there. We'll say this is a 2p. It's got 1 electron, and then the other one is going to be perpendicular to it. Okay, so the other one is going to look like this. So I'll just draw the red lobe in the back. And if you want to, you can kind of draw it like this to say it's going in the back. And say the blue lobe is coming out in front. So we'll shade it in like this. And then we'll just write 2p on it and say it's got an unpaired electron like that. So now we've got our sp hybridized carbon, and we can put 2 of these together to make a molecule of acetylene or ethylene. So if I copy this and I paste one over here, okay, and I overlap these 2 guys right here. Now there's a problem because I have to have these 2 electrons, one spinning up and one spinning down, but there's the first sigma bond, okay? So then I'm going to put a hydrogen over here, okay? So this is 1 hydrogen. This is the other hydrogen. Remember, hydrogen is 1s1, so this is a 1s orbital. This is a 1s orbital. And then my 2 pi bonds, the first p orbital is going to be touching here and here. And I'll use my green pen for the one in the back. It's going to be touching like this and then like this. So what I've just drawn is the orbital overlap diagram for this molecule. Okay? All I'm doing is drawing this molecule, but I'm showing you the orbitals that are being used to make the molecule. So there you go. And this molecule, again, this is called acetylene or ethine. Either one is totally fine. So there you go. So that explains hybridization. And so based off of that, let's see if we can answer a question. So to rehash, if we have a carbon that has 4 bonds, 4 single bonds, it's sp3 hybridized. When it's got a double bond and 2 singles, it's sp2. And when it's got a triple bond and a single, it's sp. Okay. But this, sorry, sp. But this is all based off of steric number. So there are other scenarios as well. Okay, so this is based off of steric number. So if your steric number is 4, it's sp3. If it's 3, it's sp2. If it's 2, it's sp. So I'm going to highlight a carbon, and I want you to tell me what its hybridization is. If I highlighted this carbon in yellow, what's the hybridization of this guy? sp3, sp2, or sp?
SP.
Yeah, it's sp, right? Because it's got it's got a steric number of 2, right? It's got a triple bond and a single bond, so therefore it's sp. So this guy would be sp, as would be this guy, this guy, this guy, and that's it. I just have one more to ask you about. Okay, if I put a red circle around this one, it's not a trick question. Could anybody tell me the hybridization of this carbon and with the red circle on it? Again, I'm not trying to fool you or anything. Go with your gut. It's got a steric number of 2. So it's sp as well. Exactly. So this one is sp as well. Okay, remember, the steric number, a single bond counts as 1, a double bond counts as 1, a triple bond counts as 1, a lone pair counts as 1, and an unpaired electron counts as 1. So you've got 2 double bonds, so that's 1 plus 1, which is 2. Steric number is 2, so therefore this is sp hybridized. All right, what if I highlighted this carbon in red? Could anybody tell me what the hybridization of this one is? It's sp2, exactly. So then this guy will put sp2. We could highlight this one as sp2, and this one is sp2. Now all the rest of the carbons, let me fix that. So sp, 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 sp. So these ones are all sp. Then we had this one, and this one. These ones are all sp2. And then all the other ones, this carbon, son of a gun, need a different color. Let's try green. These 3 are all going to be sp3. Why? Because they all have 3 single bonds. So sp3, like that. All right. So there you go. Give me a thumbs up if you're with me on hybridization. Cha? All right. So let's try it with the oxygens then. So what's the hybridization of this oxygen here with the black circle around it? It's sp2, right? It's got a steric number of 3, so sp2. Whereas this one here, what's its steric number? Two lone pairs, 2 bonds. It must be sp3. Right, there you go. So to review for the 3rd time, if you have a triple bond, that counts as a steric number of 1. A double bond counts as 1. A single bond counts as 1. A lone pair counts as 1. And an unpaired electron, they all count as 1. Now, as far as bond length and bond strength goes, this is something that always comes up on the first quiz. It always comes up on the final exam. And students are usually very good at figuring this out, is that as you increase the number of bonds between 2 carbon atoms or between any 2 atoms, the bond length gets shorter and shorter. So you see here, as we go from a single bond to a double bond to a triple bond, you notice that the bond length goes from 1.54 down to 1.34 down to 1.20 angstrom. Remember, an angstrom is just 10 to the negative 10 meters. And yeah, so you see that they get smaller. The reason for that is because you have more orbitals overlapping, and atoms have to get closer and closer to have efficient orbital overlap. And then as far as bond energy goes, you can see that they get stronger and stronger and stronger, right? Well, that makes sense, right? Bonds have the strength, right? It takes energy to break a bond. So the more bonds you have, the stronger the bond is going to be. So bond energy is increasing. So increasing. And as we increase the number of bonds, the bond length is decreasing. Decreasing. All right. So with that in mind, if I call this bond, I'll call this one A, and I'll call this one B, and I'll call this one C. We'll go from longest to shortest. Which one of these is going to be the longest bond? A, B, or C?
A.
Yeah, absolutely. And then the one that's going to be the shortest would be Yeah, it's going to be C. Yeah, because A is a single bond, B is a double bond, and C is a triple bond. So it's going to be A is the longest, B somewhere in the middle, and then C is going to be the shortest one of all. You can also look at the hybridization here, right? This carbon is sp3, as is this one. These ones here are sp2, okay? And then these two guys here, these are sp and sp. All right. So before we tackle molecular geometry, why don't we take another short break?